How fast does electricity flow? That's the question. Well, it depends on what you mean by electricity. The word electricity has more than one meaning. So before we can talk about its flow, we have to decide on which of several electricities we really mean. Today we will be talking about electric current. Okay, then how about this? What is electric current? It's the rate at which charge flows. A large current, such as that used to start a truck engine, moves a large amount of current in a small time. Whereas small current, such as that used to operate a calculator, moves a small amount of charge over a long period of time. So how fast does this something move? When we turn on a flashlight, something called an electric current begins to happen. Inside the flashlight bulb, the thin filament wire gets hot because there is electric current in the metal. This current is a motion of something. So how fast does this something move? Electron sea. So electrons in electron sea are free to flow and carry electron current. Inside the wires, the something moves very, very slowly, almost as slowly as a minute hand on a clock. Electric current is like slowly flowing water inside a hose. Electric charges typically flow as slowly as a river of warm putty. And in AC currents, the moving charges don't move forward at all. Instead, they sit in one place and vibrate. Energy can only flow rapidly in an electric current because metals are already filled with this putty. If we push on one end of the column of putty, the fire end moves almost instantly. Energy flows fast, yet an electric current is a very slow flow. Within all metals, there is a substance which can move. This stuff has several different names: the sea of charge, or the electron sea, or the electron gas, or charge. We often call it electricity, and state that electric currents are flows of electricity. Calling it electricity can be misleading because many people believe that electricity is a form of energy, yet charge is not energy, and currents are not flows of energy. During an electric current, the metal wire stays still, and the sea of charge flows along through it. When the flashlight switch is turned off and the light bulb goes dark, the charge sea stops moving forward. Even though it stops moving, the charge sea is still inside of that wire. And the flashlight is again turned on, but then two light bulbs are connected in parallel instead of one. As you can see in the picture, the electric current will have twice as large a value once it's connected in parallel instead of just one. And most importantly, the charge C within the battery's wires will flow twice as fast. So in other words, the speed of the charge is proportional to the value of electric current. Small current means slow charge flow, and large current means high speed. So zero current means the charges have stopped in place. So we know that charges speed up whenever they flow into a thinner wire. The high current in a large flash lantern's light bulb would be much faster than the same current in the other conductors in the lantern. Even though an electric current is a very slow flow of charges, we can't know the actual speed of flow unless first we know the thickness of the wires, as well as the value, the amps, of the current in the wires. If a thin wire is connected in a circuit end to end with a thick wire, it turns out that the charges in the thin wire will move faster. This makes sense. It just works like that when water in rivers go through charges, they move faster. If a huge wide river moves into a narrow channel, the water will speed up, versus when the channel opens out again downstream, the water will slow down. So the electric current inside a very thin wire will tend to be faster, even if the value of current is fairly low. This means that we can't know the speed of the flowing charges unless we know how thick or what the cross-sectional area of the wire is. So if we go on to the next slide, we can see that this is an example of just like the water example. So we see at the base of the lift, the skiers are really crowded. There's so many of them. It's a wide area, and they're moving really slowly. But we know that once you get on the lift, it becomes a narrower path and more skiers can move faster through this. So we see this trend when electrons are flowing. This is another skiing example. You can see the video. So once on the lift, the skiers represent charges moving throughout, like through a wire. Even though the chairlift itself is moving really slowly, the amount of skiers that are moving up the mountain is a lot because each chair holds about 4 skiers. So the chairlift represents the wire and the skiers represent charges. From what we have learned so far, it's that moving charges create currents. So what we've learned so far is that each wire that conducts the flow of electrons produces a usable electric current. And these currents are composed of billions of atoms. And to move it along, the electrons have to traverse these atoms, randomly zigzagging their way. As they do, resulting in the net flow rate, this is called the drift velocity. But how slow, really, is the velocity of a current? So to calculate it, we use this formula. I equals N times A times B times Q, or V equals I divided by N times A times Q. So I is the current, N is the number of electrons per cubic meter, A is the cross-section of the wire, and Q is the charge of an electron, and V is the drift velocity of the electrons. Since the number of electrons in a copper wire is about 8.5 times 10 to the 28th per meter cubed, and the charge of an electron is 1.6 times 10 to the negative 19 coulombs. If we also know the cross-sectional area and the current, we can calculate the electron's drift velocity, also known as the speed of an electric current. So for example, if you have a current of 14 amps, and you had a copper wire with a cross-section of about 3 times 10 to the negative 6 meters squared. If you plug in all those numbers to the formula we just saw, you get that the electrons are moving at a speed of 3.4 times 10 to the negative 4 meters per second, or about a whopping 1/3 of a millimeter per second. To put those values that are easier to conceptualize, this works out to about 1.2 meters or 4.1 feet per hour. That's a rate about 195 times slower than the average box turtle, which can cover about 800 feet in that same amount of time. Pretty slow. So how is it that something that makes a turtle look like the Roadrunner can more or less instantaneously turn on a light across a room? Chain reaction. The atoms in the wire are crammed together cheek to jowl, which, while it makes the going slow, also has the electrons more or less bumping into one another. So when the switch is turned on the light bulb, thanks to the electrical potential difference created by the generator, a force is created to move the electrons, with each pushing on each other will create a force and a current. And then this is how you can determine current speed.